Independence. A and B are independent events if the occurrence of A does not affect the probability of B. So there are 4 ways that we can determine if A and B are independent events. If you find the probability of B, given that A happens, it's going to be exactly the same thing as just the probability of B. Similarly, A and B are independent if when you find the probability of A given B, that will just equal the probability of A. Number 3, the probability of B given A is the same as the probability of B given not A. Oops, and I don't think we're using that notation, so let me write not A. So if those are the same, given that A happens, or given that not A, or the opposite of A happens, if those are the same, that means A and B must be independent. And then if the probability of A and B is equal to the rule that we learned last time, the probability of A times the probability of B, then that would mean that those 2 events are independent. So recall the example that we were working on before with the contingency table that shows the type of person in a traffic fatality. And we want to know, are the events female and driver independent? So there are a couple of ways that you can do this, but using those 4 possibilities that we just went over, to see if female and driver are independent, I'm going to look at the probability that a fatality was female given that the person was driving. Well, if these are independent, that would mean that this would equal just the probability that the fatality was female. Okay, so that's what I want to determine. Okay, so let's start with the probability that the fatality was female given that the person was driving. Well, using our definition, this is equal to the probability that the person was driving and female divided by the probability that the person was driving. Okay, so that would equal, the probability somebody was driving and a female is 65/98 out of our total 37,479. But if you remember how these were working out on the last page, that denominator was dropping out. But just in case someone's looking at my notes and not listening to the video, I'll go ahead and write it out for clarity. Divided by the probability that someone was driving would be 27,393 divided by our total 37,479, canceling out that denominator and using our calculator, this is approximately 0.241. Okay, well now let's look at the probability that the fatality was female. Well, there were a total of 11,494 females out of a total of 37,479 fatalities. And when I do that arithmetic, I end up with 0.307. So those 2 values are not equal. So that means that these are not independent. Knowing that the person was driving does affect the probability that the person's female. Okay, going on to our next example. The U.S. National Center for Health Statistics compiles data on injuries and publishes the information in Vital and Health Statistics. A contingency table for injuries in the United States by circumstance and gender is as follows. Frequencies are in millions. Okay, so people injured at work we have males and females who were injured, and let's see if they were injured at work, at home, or other. Is the event that an injured person is male independent of the event that an injured person was hurt at home? Explain your answer. Okay, well again, we have to prove one of those 4 cases that we talked about earlier. So I want to check if the probability that the injured person was male, let's say given that the person was injured at home, we would need to check to see if this is equal to the probability that the injured person was male. If these are equal, then that means that these are independent events. Okay, so let's start with our conditional probability. Okay, the probability that the injured person was male, given that he was injured at home, is equal to the probability that the person was injured at home and was male, divided by the probability that he was injured at home. So using my table, okay, so the probability that he was injured at home and male was 9.8. It's in millions, but that won't matter when we do our computation. Out of a total of 61.4 million, divided by the probability that someone was injured at home, 21.4 out of 61.4. Again, all these are in millions. So the 61.4 will cancel, and then use your calculator to get this to, let's do 3 decimal places, and that should give you approximately 0.458. So now let's look at the probability that the person injured was male. So let's see, males, there were a total of 35.6 million injured males out of a total of 61.4 million injured persons. And when we approximate that to 3 decimal places, we get 0.58. So again, we end up with 2 values that are not equal. So that means that these 2 events are not independent. They do affect each other. Okay, going on to the next page. So now we know enough to come up with our general multiplication rule. For events A and B, and it doesn't matter whether they're independent or dependent, the probability of A and B will equal the probability of A, and it's not just times the probability of B, it's going to be times the probability of B given that event A happens. Okay, we've seen that when they're independent, if A and B were independent, this probability would just be the product of probability of A times probability of B. But remember, we said if they're independent, the probability of B given A would just equal the probability of B. So this is our general multiplication rule that will always work. Okay, so keep that in mind as we do our next example. The probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? Okay, so gets pulled over. I'll let that, I'm not going to use a P because we don't want that to get confused with our probability. I'm going to let U represent pulled over, and let's let T represent that they get a ticket. Okay, so we're looking for the probability that both happen. Okay, well, what are we given in the problem? We have the probability that a driver who is speeding and gets pulled over is 0.8. So we're given the probability that someone is pulled over is 0.8. And we have the probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. Okay, so the probability that a driver gets a ticket, given that they're pulled over, is 0.9. All right, well, then to get what we're looking for, we can use our general multiplication rule. We need to find the probability of u times the probability of t given u. And fortunately, both of these are values that we were given. So we end up with 0.8 times 0.9, which is equal to 0.72. Okay, next we want to look at creating probability trees. Probability trees give us a way to visually represent an event space and compute conditional probabilities. So for this example, in an introductory statistics class, the number of males and females are as shown in the frequency distribution table below. Okay, so we see that there are 17 males and 23 females in this stat class. 2 students are selected at random from the class. The first student selected is not returned to the class for possible reselection. Okay, it's not returned. So the first student, that is, the sampling is without replacement. Find the probability that the first student selected is female and the second is male. Okay. Well, using a probability tree to illustrate this, we start off with the first possible selection. Okay, the student's going to be either male or female. Okay, well, what was the probability that the first student chosen was male? It would be 17 out of 40. Okay, the probability that the first student chosen was female would have been 23 out of 40. Okay, well now, what is the possibility, assuming that a male was chosen, for the second student? Well, after the male is chosen, the second student could also be a male, but could also be a female. And now, what is the probability of each of those? Okay, well, the probability that another male would have been selected, and remember that once the first male was chosen, they're not returned for a possible reselection. So that means now we have 16 men. Okay, so there's 16 possible males left, and the total is now 39, right? Because that initial male is gone. Okay. Similarly, looking at the probability that given that male was selected, what is the probability that a female would be selected second? Well, there's still 23 to choose from, again out of a total of 39 students that remain. Okay, well, the second case is the one we're actually interested in. We're looking for the probability that the first student selected is female and the second is male. Okay, so we know that this breaks down into 2 cases, male and female. This is the one that we're interested in, though. So what is the probability, given that the first student selected was female, that we now have a male? It would be 17 out of 39. Okay. So now, to get our answer, what is the probability that we choose a female and then a male? what you're going to do is just multiply across the branches. So we end up with 23 over 40 times 17 over 39. So let me just make it clear that this is the branch we were interested in. And let me go ahead and write in our probability for 2 females being selected. That would have been 22 out of 39. Okay, so when we do that product, you multiply across. So we end up with 391 over 1560, which is approximately 0.251. Okay, our next example. Suppose that 2 cards are randomly selected from a standard 52 card deck. What is the probability that the first card is a club and the second card is a club if the sampling is done without replacement? Okay, so we can do this like a tree diagram. So for the first card, we know that there are 4 possibilities. We're interested in a club, so I'm going to put that one on the top. But we know it could also be a heart, could also be a diamond, could also be a spade. Okay, well, what are the chances of selecting a club on the first draw? Well, 13 of the 52 cards are clubs. Well, that's going to simplify to 1/4. But let me just note over to the side, 13 out of the 52 cards are clubs. Okay, well, given that that first card is club, we're looking for the possibility that the second card is also a club. So we know, again, there are 4 possibilities. We're interested in the club, but it could also be a heart, a diamond, or a spade. But I can just worry about the branches that I'm interested in. Okay, so what would be the possibility that the second card is a club, knowing that there was no replacement? Well, there would be 12 clubs left, since my first one was a club, and there would no longer be 52 cards. There would actually only be 51 cards left now. So to get our probability, we multiply. So 1/4 times 12 over 51. Can do a little simplification. And we get 3 out of 51, which simplifies to 1 out of 17. Okay, going on to our second example. What is the probability that the first card is a club and the second card is a club if it's done with replacement? Well, our picture is going to look the same. It's just that that second probability is going to look different. So if the first card was a club, it would be a 1/4. And let me just draw just a little picture here just to make it clear. So we have our club and then we have our other options. And then for our second draw, we want the club, and we know there are other options. Okay, well, to draw a club at first, the probability is 1 out of 4. So if that card is put back in the deck, because that's with replacement, then the probability of getting a club on the second draw is also 1 out of 4. So now we just multiply those two together, 1/4 times 1/4, and that'll give us 1/16.